Section 8.4, Transformations and Congruence. What you'll learn: to describe a sequence of transformations that maps one figure onto another, and to determine whether two figures are congruent by using a sequence of transformations. Why learn this? When you walk in the sand, you leave a trail of footprints that are congruent to each other. You can use transformations to map one footprint onto another. And a check of the skills you'll need. Number 1, vocabulary review. The blank is the number of degrees a figure rotates about a fixed point. And numbers 2 through 4 give the coordinates of the image of each point after being rotated the given number of degrees about the origin. If two figures are congruent, then a transformation, or a sequence of transformation, will map one figure onto the other. Here's an example. Recognizing a series of transformations. The three trapezoids are congruent. Describe the sequence of transformations that maps wxyz onto w double prime, x double prime, y double prime, z double prime. Well, let's consider the figure here at the right. wxyz in quadrant 2 first moves to quadrant 1, and it looks pretty obvious that that is a reflection, right? We can think of the image in quadrant 2 as being the mirror image of the object in quadrant 1 as reflected across the y-axis. So that works well. So we see a reflection across the y-axis. And then it may be tempting to think of a reflection across x, but looking a little more closely, we can see that's not the case at all. For several reasons, a reflection would not work. It looks more as though we just have a translation. Remember, a slide or a glide of the polygon straight down. Looks like each vertex is directly located above its corresponding vertex. But down how far? I'd probably choose z prime. There in quadrant 1, that's the bottom right vertex of our polygon. And then I would count how far down that must be shifted in order to get to z double prime. And I chose z because it's kind of out there in the open. It's more accessible and easier to count than, well, our other vertices. So from z prime we must go down 1, 2, 3, 4, 5, 6, 7 units. And so from each vertex we would be translating downward 7 units. So that looks like our second transformation. Let's see how the book describes this in words now that we have a pretty good understanding of it visually. So let's check it out. A reflection over the y-axis maps wxyz onto that image or post image. A translation 7 units down then maps our first post image onto our second and final post image, the double prime version of our trapezoid. So to sum it all up, a reflection over the y-axis followed by a translation 7 units down maps wxyz onto w double prime, x double prime, y double prime, z double prime. And with that in mind, I would say it is double prime time for a quick check. So in our quick check problem, describe the sequence of transformations that maps w double prime, x double prime, y double prime, z double prime onto wxyz. So now we're really considering the reverse order. If you can use a sequence of transformations to map one figure onto another, then the two figures are congruent. Let's have a quick check of some vocabulary in this vocabulary tip. Two figures have the same orientation if you can use a translation a rotation or a combination of the two to map one figure onto the other. And back to our example at hand, using transformations to determine congruence. The problem says, determine whether the two triangles in the diagram are congruent. If they are, write a congruence statement. If they are not congruent, explain why. So we should have a careful look at the two triangles, triangle ABC in quadrant 1 and triangle XYZ in quadrant 3. Consider what we would have to do and possibly even mentally manipulate or move triangle ABC. Try and get it to overlap triangle XYZ. Remember, we can reflect, we can rotate. So I notice right away that if I were to rotate triangle ABC just slightly with a center of rotation at vertex C, and by slight rotation I mean maybe 30 degrees, definitely not a full 90-degree rotation, then it becomes oriented very similarly to triangle XYZ, but I notice these triangles won't be the same. It's a very subtle difference, but note that vertex B does not correspond to vertex X. In these two triangles, it looks as though vertex B must correspond to vertex Y, which means a reflection is in order. It says triangle ABC and triangle XYZ, and pardon the quick interruption, I believe where I left off, we just reflected triangle ABC across the y-axis. That seems like a good place to pick up. I hope I haven't skipped anything. Then notice it looks like possibly a rotation. A rotation and a translation could get us right where we need to be. Let's move on just a bit. We'll see on the next page a couple more transformations and see if this series leads us to triangles that line up very well. Of course, doing a problem like this on your own, you wouldn't have these images. Your job would be to construct images like these on your own coordinate plane and determine if the triangles truly do map to one another. So let's move on. So this is good. Check it out. If we rotate our triangle, our reflection across the y-axis, the blue triangle here, A prime, B prime, C prime, we rotate 90 degrees and then translate, we do get a perfect mapping, and so therefore these triangles are congruent. Here's how the book states that. A reflection over the y-axis, followed by a rotation of 90 degrees about the origin, followed by a translation 1 unit down, maps triangle ABC onto triangle XYZ. So, triangle ABC is congruent to triangle XYZ. Kind of a fun problem. It's almost like a puzzle, and our job is to find the series of moves that maps one of the puzzle pieces directly onto the other puzzle piece. Of course, had it not mapped perfectly, the answer would be that these two triangles are not congruent. And a quick check along the same lines of the previous example problem. Determine whether triangle EFG is congruent to triangle MNP. If the triangles are congruent, tell what sequence of transformations will map triangle EFG onto triangle MNP. Then write a congruence statement. If they're not congruent, explain why. I'd like to take a quick glance back at the congruence statement in the example problem. I feel like I went through that a little quickly, and that's worth revisiting before you complete this quick check problem. So here we are. Consider the congruence statement at the very bottom. I just want to remind you that in a congruence statement, the order of the vertices, well, it really does matter. Triangle ABC could be written in any order we'd like. It could be referred to as triangle ABC or triangle BAC or CBA. Once triangle ABC's vertices are written in some order, then it does become very important, the order of the vertices of triangle XYZ. We must write these vertices as they correspond to the vertices in triangle ABC. So what I mean by that, consider vertex A, and then consider vertex X. X is the post-image version of vertex A. So after all three of our transformations, our vertex A ended up at vertex X. Therefore, they're corresponding and must be written in the same position in the congruence statement. Notice the same with B and Y, and also C and Z. Again, I feel I kind of glossed over that, so I wanted to review before asking you to respond to the question. And I won't go over this much more. Here it is, number 2. And finally, your section 8 for Check Your Understanding problems.